equation for the response, for the free response, of course, can be written in this form. X of t is equal to x exponential minus zeta omega nt sine omega dt plus phi. So we have two main important parameters here, which are the exponential minus zeta omega nt. This is the envelope, the green one, the green dotted line here, that is decaying when the time goes to infinity. This term, exponential minus zeta omega nt, when t goes to infinity, this term goes to zero. So this tends to zero when t tends to infinity. And with increasing time, this will go to zero. And we have another sine term, sine or cosine, depending on the initial conditions and the arrangement you make for the two parameters. So the sine term will be built in or superimposed inside the envelope. So it will be decaying. You can see here also that we wrote, if you remember, we wrote the poles for the characteristic equation. We wrote them in this form: minus zeta omega n plus j omega d. This is S1. S2 is the complex conjugate, which is minus zeta omega n minus j omega d, where omega d, we defined it like this. Omega d was equal to omega n square root of 1 minus zeta squared. This is, we call it omega d. So we have two complex conjugate poles, as you can see, S1 and S2. And this, the real part of the pole, the real part minus zeta omega n, is responsible for the decay, for the decaying rate. So exponential minus zeta omega n, the real part, is responsible for the decay. While the imaginary part, which is omega d, or omega n 1 minus zeta squared, is responsible for the sinusoid, which is this one, omega d. So the two term, the real part is responsible for the decay. The omega d is responsible for the sinusoid. So these are the parameters when zeta is less than 1, when the system is underdamped. So this is for the case of underdamped system. When zeta is less than 1, we wrote it in this form. So a few remarks here. The poles are located here, zeta S1 and S2. The real part is minus zeta omega n. The imaginary part is omega n 1 minus zeta squared. So the response is decaying sinusoid. The response, we were talking about this. With time, it is decaying. So this is t, and this is x of t. When, of course, here we have zeta is less than 1. The frequency of oscillation is omega d equal to omega n 1 minus zeta squared. And for positive damping, if you see, for positive damping, here we have any meaning a new zeta is greater than 0, but still less than 1. That's why it is positive. So the poles S1 and S2 have negative real part. The real part will lie here in this region. It could be here, here, here. It could be in any region in the left-hand side of the complex plane. So in this region. So the real parts lie entirely on the left half of the complex plane. As a result, the transient response decays with time and the system is said to be stable, which means that the finite value will be a finite value. When t goes to infinity, the response will go to a finite value. Now, the rate at which the transient response decay depends on the zeta omega n, as we mentioned here, on the real part. This is the real part in exponential minus zeta omega n. So larger zeta omega n means smaller 1 over zeta omega n leads to a faster response. So if you have zeta omega n large, means that the system goes faster to the steady state response, or it goes to 0 faster and faster. So the term also 1 over zeta omega n is called the time constant. of the second order system. Therefore, the time constant for the second order system can be made smaller by moving the real part to the left. So the damped, critically damped system, when we have the critically damped system, zeta is equal to 1. The system is critically damped. And we have seen that we have, in this case, two poles, S is equal to, S1 is equal to S2 is equal to minus zeta omega n. Because if you remember, we wrote the pole, we wrote them like this, S1, 2 equal minus zeta omega n plus or minus J omega n 1 minus zeta squared. When zeta is equal to 1, this term is 0, and this one will be 1, so S12 will be equal to minus zeta, minus omega n, because zeta hina is equal to 1. So the poles will be lying here, and the response will look something like this one. The response will look like this one. The equations can be written in this form, like we did exactly in the same case for zeta is equal to 1. And we can write the expression for x of s. We can write it like this. We do the same steps we did for the underdamped, and we end up by having, this is the response when we write it in partial fraction, here like this. So this one will be x0 exponential minus omega n t, and this one will give you omega n x0 plus x dot 0. These are the initial conditions. And 1 over s squared is simply t squared. Sorry, is t. When you take the inverse Laplace transform, it will be t. But it is shifted with minus omega n. So the response will look something like this. x0 exponential minus omega n t plus omega n x0 x dot 0 t exponential minus omega n t. This is the equation for the response, and the response will behave like this. As you can see, the response, Shabab, will not oscillate, which means it does not go below the line 0. It does not go this way like for the critical, for the underdamped case. So the response for the underdamped case, it was doing this way. But here it will not go beyond this line. It will not go below. So the response will not oscillate. It will just go to the steady state without oscillating. Here we are taking the case of critically damped case, and we are changing the values of omega n, the natural frequency. Omega n is equal to 0.2, omega n is equal to 0.5, 0.7, and so on. And we are also fixing the initial conditions. We are taking x0 is equal to 0.5, which means from here to here is 0.5. And the slope, which is our velocity, is equal to 0, which means all they have slope x is equal to 0. This is the critically damped case when zeta is equal to 1. So critically damped case are systems with the smallest value of damping rate that yields aperiodic motion, means the motion will not be periodic, which means it does not repeat itself. Critical damping can be also thought as the case that separates the non-oscillation case from the oscillation case for the value of damping that provides the fastest return to 0 without oscillation. So it goes to 0 without oscillation. Remember, this is the critically damped case. So if a system with critical damping is displaced, it will return to its equilibrium position as quickly as possible without even passing through the equilibrium position. This is called the critically damped case. The overdamped case, when zeta is greater than 1, the poles here, we have seen that they are real and distinct. S1 and S2, they are both real and distinct. So in this case, the solution will be x of t equal to this amount, x0 minus x dot 0 over this amount, exponential minus this, plus this amount exponential minus this. You are not required to memorize this equation, but all you need to know is when the poles are located here, what will be the shape of the response. The shape of the response, as you can see, it looks almost similar to the critically damped case. So when the poles are located here, this is the behavior of the response. An overdamped system does not oscillate exactly like the critically damped case, but rather returns to its position exponentially. It is returning to the exponential case here because we have the exponential minus this term, the root. Too much damping prevents the system from oscillating and no omega d to speak of here. Remember, this is the case of the overdamped case. This is the case for critically damped case when the poles are located here. This is the critically damped case. When the poles are located here for underdamped case, we found this response which is decaying. So the only case when the system is decaying or exponentially and has damped frequency is the case of the underdamped case. And this is the overdamped case response when we have x0 is equal to 0.5, x dot 0 is equal to 0, and we have omega n is equal to 2 radian per second. We are changing the values of zeta 1.2, 2, 3, 5, and 7. See how the response goes faster to the steady state value. So this is the free response. And now we will see the case of the free response has special attention also to take. The free response, Shabab, when we have zeta under damped case, which is this case here, and the motion either it's free response, or also the impulse response. For the impulse response, we also obtain this case, if you see. Now, there is one method to use this one called the logarithmic decrement. When the response is behaving like this, we can establish a relationship between the amplitude of the consecutive amplitude. We can establish a relationship between them, this consecutive amplitude. Suppose that at time t1 is equal to t1, we had amplitude x1. At time t2, we had amplitude x2. At time t3, we had amplitude x3, and so on. So this is what we have here. At time t4, we have amplitude x4, and so on. So we try to find relationship between this amplitude to find the mass, for example, of the system, to find the damping or the dashpot element, and to find the stiffness just from this signature. If we can find this relationship, we'll be able to find what is the mass, what is the damping, and what is the stiffness for the system. So this method is called logarithmic decrement method, which is experimental method, because in the experiment, you do your experiment and you obtain this response. But unfortunately, you don't have the parameters. You don't know the parameters of your system. So this is an experimental way how to find these parameters using the logarithmic decrement. Is this clear, Shabab? So far, is it clear?
Yes, clear, Doctor.
Shabab, did you receive the textbook? Shabab, did you receive the textbook? No. No email, nothing. Because the chairman is asking if you received the textbook. Yusuf. Okay, Shabab, thank you. So this is the experimental method to find the mass, spring, and damper system. Not only mass, spring, damper system, but you can find the resistor, capacitor, and inductor. But since we are mechanical engineers, we are showing you this one. So basically, it's experimental method. You do your experiment, you obtain a response like this, and you would like to see what is the amount of damping, and what is, you can see also what is the natural frequency, what is this mass spring damper system. So the equation for the response, Shabab, we wrote it either in this form, or we wrote it also in this form also. It can be written also in this form. X of t is equal to a constant exponential minus zeta omega n t sine omega dt plus phi. So either this or this we can apply. So now at t1, at t is equal to t1, we have x1 equals c exponential minus zeta omega n t1 cosine omega d t1 minus phi. Just substitute time by t1. At another amplitude x2, we substitute simply x2 is equal to c exponential minus zeta omega n t2 cosine omega d t2 minus phi. So this is for t1 and this is for t2. Now, if we take the ratio x1 over x2, we will have exponential minus zeta omega n t1 cosine this over exponential minus zeta omega n2 cosine omega dt minus phi. Now, Shabab, we look at this guy here, we look at it. Cosine omega d t2 minus phi. T2 here, Shabab, if we take this is t1, and as you can see, this is a periodic function, and with the period 2 pi. So if we take the peak-to-peak amplitude will be the period. Peak-to-peak will be the period, for example. If you take the peak-to-peak, so from here, from this peak to this peak will be the period. So we can write it like this. Td will be 2 pi over omega d. So T2, can you tell me T2? T2 will be equal to T1 plus tau d. Do you agree with this? Where tau d is the period. So the time T2 can be calculated as T1 plus the period tau. Is that right, Shabab? T2 will be equal to T1 plus the period tau d. So this is what we are writing. We are writing in a substituting this T2 by omega d T1 plus Td. This is T2, the time. Now, we can say this one will be cosine omega d T1 plus omega d Td minus phi. So, here, Shabab, if you look to this expression, omega d, or we are writing omega d Td, we are writing tau, or the period T, will be equal to 2 pi over omega d. Now, if you cross multiply, you will see that tau d omega d will be equal to 2 pi. So we are simplifying this by 2 pi. So I will have omega d t1 plus 2 pi minus 5. Now, this is a cosine function, and the cosine is a periodic function with a period 2 pi. With a period 2 pi means if we the function is with the period 2 pi means, and we have cosine, any cosine t plus 2 pi will be equal to cosine t, because the function is periodic with period 2 pi, which means here this is not the cosine, but I will draw the cosine here, or sine, it doesn't matter. Sine or cosine is the same thing. So if you take a value here, this is t, and after 2 pi, you take this one, this is t plus 2 pi. They will have the same cosine here. They will have the same value of the cosine. So t or t plus 2 pi, they will have the same cosine. This is what it means, periodic and period 2 pi. So we instead of having omega d t1 plus 2 pi, it will be simply cosine omega d t1. So if this is cosine omega d t1, we can simplify this with this, and then we will have the ratio. It will be exponential zeta omega n t2 minus t1. Exponential zeta omega n t2 minus t1. So this t2 minus t1, if you look at t2 minus t1 from here, it is simply the period, td. So we can say td will be simply the time t2 minus t1, which is exactly the same. So if we take this ratio, we can write it like this. We define the logarithmic decrement, we define our expression here, we define the logarithmic decrement. This one will be, now if you take the log of this len here, len of x1 over x2, it will be what? It will be zeta omega n td. So if you take the len, it will be zeta omega n td. So the next slide, you will see the logarithmic decrement. We define our delta as the logarithmic decrement to be any two successive amplitude, displacement amplitude. So it will be delta is equal to len x1 over x2 is equal to zeta omega n td. Now, you substitute td by 2 pi over omega d. Td is equal to 2 pi over omega d. And you substitute omega d by omega n. Omega d is equal to omega n 1 minus zeta squared. So this is omega d. You simplify here, this is 2 pi over omega d. This is omega d. All this one is omega d. You simplify omega n with omega n, and you end up by having delta will be 2 pi zeta over 1 minus zeta squared. So what you will do, you will take the amplitude of the first amplitude, the magnitude of x1 over the amplitude x2. You take the logarithmic decrement, this will be called delta. So this delta will be equal to this delta will be equal, you know it, because from the length, it's x1 over x2, you know it. So you measure x1, you measure x2, take the logarithm, and this will be delta. This delta is equal to this, 2 pi zeta over 1 minus zeta squared. Now, we can solve the other way around. We can solve for zeta, and we will find the amount of damping from here. So if we have this equation, delta, if we have the equation in terms of delta, خلاص, delta, we found it. It's given value. We found it from the logarithm of the first amplitude over the second amplitude. We found this value. It is equal, this one will be equal to 2 pi zeta over 1 minus zeta squared. Now we solve for zeta. When we solve for zeta, we find this. We find the value of the logarithmic decrement, which is even, or we find the damping ratio. Sometimes, Shabab, when the damping is very small, for a very small damping, the amount 1 minus zeta squared can be equal to 1, yani in case of damping very small. For very small damping, this one can be 0, zeta square will be 0, and this one, 1 minus zeta square, can be assumed to be 1. And this one, hina, or this expression, hina, it will be simply 2 pi zeta. When you simplify it, it will be 2 pi zeta for small, very small damping. So the equation for very small damping, delta is equal to pi zeta, is in the red one, this one here, and delta from here is given by this expression. So you see, almost when you have zeta is equal to 0.3 up to zeta 0.3, all the values are equal. This is the nonlinear expression, which is 2 pi zeta over 1 minus zeta squared, and this is the linear one, delta is equal to 2 pi zeta. So this is what we have here. Now we can express it. This is but to act to the condition that we should have the successive amplitude. Successive amplitude means, and we know x1 over x2, or ln x2 over x3, or ln x3 over x4. So the amplitude needs to be successive, one after the other, or ln xn over xn plus 1. So one over the other, successive amplitude. This amplitude over this one. So x1 over x2, or x2 over x3, or x3 over x4, and so on. So they need to be successive. We cannot use this formula if we have only this amplitude with this amplitude. They have to be successive, yani one after the other. But what will happen, Shabab, if we have uh, non-successive amplitude, like the case here? Like the case here, we have x1 and we have xn plus 1, for example, here. Xn plus 1. We can use we can use x1 over xn plus 1 to be x1 over x2 times x2 over x3 times x3 over x4 times x4 over x5, and so on. So, and we can use, if you remember, the logarithmic decrement or the logarithmic expression log a b c is equal to ln a plus ln b plus ln c. We can use this formula. So if we can use the ln here, this will be ln of x1 over x2 plus ln x2 over x3 ln x4 over x5 and so on, ln xn over xn plus 1. So if you look at this one, we already defined it to be delta. And this one, we already defined it to be delta. And this one is delta up to n delta. At the end of the day, we will have n delta. So n delta will be equal to ln x1 over xn plus 1. And at the end, we will have delta will be equal to 1 over n ln x1 over xn plus 1. So if you know the first amplitude and the amplitude number n or any amplitude, so this is the case. 1 over n, n is the number of cycles, ln x1 over xn plus 1. So this is when the non-successive amplitude are given. Yes, تفضل. Yes, تفضل. Who is talking, شباب؟ مين؟ تفضل. Who is يا شباب؟ مين حاب يتكلم؟ تفضل. It's okay, no problem. So the table of logarithmic decrement of some various types of structures, we have multi-steel buildings between point zero 0.02 to point 0.1. This is the delta, Shabab. You should not make a mistake between delta, the logarithmic decrement, and zeta, which is the damping ratio. This is damping ratio, and this one is the logarithmic decrement. This is logarithmic decrement. So steel bridges between point zero 0.05 to point 0.15, multi-story concrete building between point 0.1 and point 0.2, concrete bridges between point 0.1 and point 0.3, machinery foundations between point 0.4 and point 0.6. We have an example here, Shabab, to be solved. Of the free vibration response of certain system which has a weight or a mass of 1000 kilogram. After 5 cycles, the amplitude of displacement is 10% of the first amplitude. Okay. Also, the time for the 5 cycles to occur was measured to be 20 seconds. Estimate the damping C and the stiffness K. So they gave us only this information, and from this information, they want us to find the damping amount B or C and the stiffness K. So we will use this one here. If you see N is equal to 5 cycles. So this is N. And now we will see, Shabab, we will take this one from any point we can start. We can take this one will be X1, X2, this is one cycle, X3, this is another cycle, X4, another cycle, X5, another cycle, and X6, another cycle. So from X1 to X6, this is N is equal to 5 cycles, 5 cycles. So this is a 5 cycles, but with this is X1. When we go up to 5 cycles, so we will go to Xn plus 1. So this one will be X6. Then the logarithmic decrement, we wrote it like this. We wrote it delta will be equal to 1 over n ln X1 over Xn plus 1. So n will be equal to 5. The Xn plus 1 is X6. The X6, this one, X6 at this point is 10% of this one. Is 10% of this one. Yani if we take X6 over X1 will be equal to 0.1. واضح شباب؟ واضح؟ It's reduced by 10%. هو is saying like this. The amplitude of the displacement is 10% of the first amplitude. Yani the amplitude of this one, it is reduced by 10%. So means X6 over X1 will be 0.1. That's why we are writing in a X6 over X1 will be 0.1. So now if we substitute in the formula for delta, we have 1 over n, then X1 over X6 will be 1 over 5, this is n, and this one, X1 over X6, will be 10, لأنه reciproc of this X1 over X6 will be equal to 10. So if you calculate this one, you will find it 0.4605. And now if you solve for zeta, from the previous formula, you will find that your zeta is 0.4605. This is delta over 4 pi square plus delta square, which gives you 0.0731. This is your damping ratio. Remember, delta, we found it from the graph. Zeta, we found it from the formula. Now they gave you the time for 5 cycles is 20 seconds. Yani time for here we have the cycles, the full time is 20 seconds. So what will be the period? The period will be this full time. This is full time T. T is equal to 20 seconds. So the period tau or TD will be 20 divided by 5. The total time divided by the number of cycles. This will give you 4 seconds. So the time period will be 4 seconds. So omega d will be simply equal to 2 pi over tau d, or simply 2 pi divided by tau d, or td will be 4. This td, which will be 4, it will be pi over 2. On the other hand, Shabab, here, this pi over 2, which is pi over 2, omega d is equal to pi over 2. It is equal to omega n 1 minus zeta square. 1 minus zeta square. Zeta is known. Zeta is 0.0731. 0.0731731. This is omega n not known. Pi over 2 is known. So you solve this equation, you solve from here, you solve for omega n, you will find omega n will be 1.576 radian per second. So omega n will be equal to 1.576 radian per second. So once you know omega n, k, if you remember, since we have a mechanical system here now, and usually we define our natural frequency, omega n, to be k over m. So omega n will be equal to square root of k over m. So m is given. Omega n, we just know it. We can say omega square n is equal to k over m. From where we can solve for k equal to m omega square n. The mass is given to you to be 1000, so k will be m omega square n. 1000 multiplied by omega n square here, you will find the mass, or you will find the stiffness to be 2483.776 Newton per meter. Now, how to find C, or the damping? It's very easy. If you remember, since we have, this is our mechanical system, in general, the mechanical system is written in this form. In this form, we can write our mechanical system, mx double dash plus bx dot plus kx is equal to 0. This is, of course, the free response. We can write it like this, x double dot plus b over m x dot plus k over mx is equal to 0. And if we compare this to the standard form can be written in this form, x double dot plus twice zeta omega n x dot plus omega square nx is equal to 0. So what we have here, Shabab, if you look, we compare between these two equations, we have this k over m is equal to omega square n and x. We already did this, and we equate this b over m is equal to twice zeta omega n. So from here, we have b over m equal to twice zeta omega n, okay? Or we just say here b will be equal to twice zeta omega n. We already calculated it, if you remember. We calculated it, or we did it k over m. We said omega n is k over m times m. You simplify m with m here, and you have twice zeta km. It will be k times m, which is this one. B, or C, is equal to twice zeta km. You substitute 2 zeta m is equal to I think 1000, and k square root of k, this one we substitute k here, the k, the value here, k will be here, and we find the value for omega for C or B. This is the damping ratio. Here the value of k is 2483.776. I'm not sure if you get the same value, but you can calculate it. But this is the way how to calculate the damp. So for unknown damping, we didn't know what is the damping. We didn't know the stiffness. We found the values for them just by knowing the shape of the signal and some information about the signal. Any question, Shabab? Do you have any question? Do you have any question? Any question, Shabab? Maybe the number will be different if you, because it looks like it's not 77, it's different values. طيب شباب, if we go to another example هنا, it says an underdamped shock absorber is to be designed underdamped. Remember, this means zeta is less than 1. Is to be designed for a motorcycle 200 kilograms, shown in the figure, when the shock absorber is subject to initial vertical velocity to a road bump. The resulting displacement time curve is to be indicated in this one here. Find the necessary stiffness. Stiffness means K, and damping constant C of the shock absorber, which is here. If the damped period of vibration is 2 seconds, the amplitude x1 is to be reduced to 1/4 in 1/2 cycle. So هنا شباب, what do we have? We don't have a full cycle, but they gave us the relationship between half cycles. So we can find the relationship between the first cycle, which is this, or the first amplitude, and the second amplitude, this one. Now what we need to know x1 over x2. But he gave us x1 over x1.5. So we can say x1 over x1.5 is reduced by 4, is equal to 1 over 4. Okay, Shabab? Is that right, or is equal to 4? So Shabab, here, remember, so this one is 1 over 4, 1 over 4 of this one. So we can write x1.5 over x1 is equal to 1 over 4. So, and x2 over x1.5, it will be reduced by 1 over 4 now. So now what do we want? We want x2 divided by x1. We can say x2 over x1.5 multiply by x1.5 divided by x1. طيب, this one شباب will be this one. This one is here 1 over 4 multiply by 1 over 4. So at the end of the day, this one will be 1 over 16. يعني x2 over x1 will be 1 over 16. So if we take delta, delta will be ln x1 over x2, x1 over x2. It will be ln of 16. Ln of 16 is simply 2.7726, and this will be equal to 2 zeta over 1 minus zeta squared. So if we solve for zeta here, if we solve for zeta, is this clear, Shabab? How did we move from here? So zeta, if we solve for zeta, we will find this value. Zeta is 0.4037. Zeta will be 0.437. He gave us the damped period, which is 2 seconds. The damped period is 2 seconds. So here, since the damped period is 2 seconds, or it is 2 pi over omega d, or 2 pi over omega n 1 minus zeta square, we can solve for omega n. لأنه omega d هي نفسها omega n 1 minus zeta square. We solve for omega n. Zeta is from here 0.037. We find omega n to be 3.4338 radian per second. The critical damping is 2m omega n, or 2 times 200, the mass is given, times 3.4338. This will give you 1373.54. And C, the damping will be simply C is equal to zeta times C. If you remember, we defined the damping ratio to be C over C critical. C critical is here. So C will be zeta times C critical, which is 554.4981. And the stiffness will be K is equal to M omega square N. And this is the stiffness. So this is the damping amount, and this is the stiffness we found it for this case. Any question? So I will stop here, and we will continue, inshallah, next time. Any questions, Shabab? If you don't have any question, I will take attendance. So this is an experimental value. If you get, for example, a multiple choice question in the quiz or in the exam, asking you the method of the, what will be the method or what you call it or whatever it is an experimental value to determine the